Good afternoon, everyone. This is Professor Neha Bura. Today we will going for the webinar on a planning and real-time application of AI, and our expert is Dr. Darshan Medhane, sir. He is an associate professor HOD in MVP KBT COE Nashik. We'll go with the introduction. Welcome, sir. Dr. Darshan Medhane, sir, formerly assistant professor with the Department of Computer Science and Engineering, Indian Institute of Information Technology, Pune, an institute of national importance established by MHRD Government of India. He is currently working as an associate professor and head of the Department of Computer Engineering at Maratha Vidya Prasarak Samaj, KBT College of Engineering, Nashik. He received the PhD degree in Computer Science and Engineering from the Vellore Institute of Technology, Vellore, India in 2018. He has authored more than 20 publications in reputed international journals like IEEE, Internet of Things Journal, IEEE Transaction of Industrial Informatics, IEEE Transaction of Emerging Topics in Computational Intelligence, IEEE Transaction on Sustainable Computing, Journal of Computers and Electrical Engineering, and etc. He is an editorial board member of and reviewer for various international SCI journal. He is a member of IEEE, IET, ACM. His research interest includes the computational intelligence, security in wireless network, cognitive data science, sustainable computing, evolution, multi-objective optimization, position monitoring system, and cyber physical systems. He is a great speaker. I welcome you, Darshan sir. Now you can start with the session. We are eagerly waiting for your session. So the mic is yours. Everyone just mute yourself.
Yeah, so very good afternoon, one and all. Am I audible, madam?
Yes, sir, you are audible. You can share your screen.
Okay. Okay, so thank you very much for this brief introduction. So to start with, may I share the screen, ma'am?
Yes, sir. Share. You can share your screen. Hello, sir. Your screen is not visible yet.
Yes, madam. Please check whether it is visible now.
Yes, yes. Now it's visible, sir.
Visible?
Yes, yes, sir.
So shall we start, madam?
Yes, sir. Definitely, we can start.
Okay, fine. Once again, thank you very much, madam. So to start with, first of all, I would like to thank the organizers of this session and for giving me this wonderful opportunity to share the things regarding the topic of today's session with all of you. So I'm very happy to share the contents with all dear students. So to start with it, this is going to be the outline of my today's presentation. So we'll start with the basics of planning, followed by planning languages, then different types of planning which are involved within the literature of artificial intelligence, which is an emerging trend of technology in these days. So we'll start with goal stack planning, followed by partial order planning and their subtypes. Then we'll go for plan space and searching in planning, followed by some real-time applications in AI. So to deal with, like whenever we think about the concept of planning, so it is quite essential for us to first of all come up with some plan. Whenever we plan some activity or we have to execute some things, in that case we have to first of all come up with some uh, genuine plans which are associated with that activity, so that we can further carry out or consider the sequence of tasks. So basically, we will like understand the concept and importance of planning, then the role of planning, the exact role of planning rather in intelligent systems, the importance of planning in autonomous agents, to understand the application and usage of planning in artificial intelligence is also one of the goal. And you will surely acquire the knowledge about the algorithms and the methods which are involved in this planning strategies from artificial intelligence. So to start with this, see, planning is required to convert the objectives into actions. So whenever we plan something, so like those things are created as the aims and objectives, what we can say, or goals, what we have to achieve during that overall process as a whole. So to convert those aims, objectives, or goals into actions, we need the planning process. And to perform any activity efficiently and effectively, so we need to plan basically. So during this session, we are going to cover the two course outcomes associated with this course as per the curriculum of Savitribai Phule Pune University and Board of Studies in Computer Engineering. So it is CO4 to apply the suitable algorithms to solve AI problems, and CO6, that is represent complex problems with expressive yet carefully constrained language of representation. So whenever we start with this planning concept, so see, every morning we plan something, like these are the tasks which are to be done throughout the day. So like after getting up, we decide the agenda and plan for that particular day. So every person has his or her own set of do's and don'ts, what we can say, or for that particular day, and accordingly we can move, like whatever is planned by him or her according to the timings of the other relevant activities, what we can say, which are associated with that particular day. So based on different constraints related to timings and other members which are associated with us or who are associated with us, so we plan the activities and accordingly we execute the activities throughout the day. So we can consider example of the examination schedule or some like timetable which we used to follow daily in our daily routine academics. So it is subject to like the things which are in plan and the timings, of course. So time is going to be the critical factor which is associated with it. And planning for studies or academics, it includes scheduling of all the subjects in such a way that the particular subject is that can be studied or that can be learned in a specified time. So it deals with the scheduling and ordering of studies, what we can say. And there are, of course, the dependencies, like some subject is prerequisite for some other subject. Likewise, we can have, like, for example, in theory of computation, the prerequisite subjects are like discrete mathematics or some other mathematical subjects or discrete structures from the computer science literature. So they are basically the prerequisites, or they are the like dependencies. Okay, and like knowledge from these subjects is quite mandatory before starting with that particular subject. So see, we have a lot of constraints, or we have lot of constraints whenever we start with the planning activities. Like if suppose now we are towards the end of this current semester, so number of days which are left for the exam, the type of subjects like theory subjects, practical subjects that you are going to study in upcoming days, within next 1.5 month. So like number of units that you need to study, the availability of notes for subjects or subject wise, what we can say, and so on. So this is nothing but what these are constraints, or these are the things or objects which will take you to the firm planning, or to the necessary planning that you have to achieve, or that is required, like to achieve some goals in upcoming future. Okay, so the goal could be to get like distinction in this case, like in attaining the examinations. So from that point of view, the goal is like what class, or whether if we need to get, or if you want to get distinction, or whether you need to just clear those subjects. So planning involves the step-by-step procedure that is to be taken to reach the goal optimally. So you might have studied the concept of optimal solutions, or the principle of optimality in unit 2 and 3 of this course. So like we can say that it determines how and when to do the necessary steps or activity whenever we are provided with some set of goals or objectives which are associated with that activity. Okay, so as it is mentioned on this slide, you can see like real world problems. The planning is nothing but the task of coming up with the sequence of actions that will achieve the particular goal or the set of goals even. Okay, so just now we have a brief case study discussion on this overall academics, and towards the end of semester now, as you are going to attain the examination. So what things you need to plan is nothing but the classic example of this planning. Okay, so like we can consider again classical planning environments, like which are fully observable, which are deterministic, non-deterministic, finite, not finite, static, dynamic, or discrete, what we can say. So in time, actions, objects, and in terms of effects as well. Okay, so problems with standard search, like they are overwhelmed by irrelevant actions, and finding a good heuristic function is quite difficult in some of the cases. Like it depends. So it, of course, it depends on the type of search strategies. That is, whether it is type of uninformed searches, like it is breadth first search, or it is like depth limited search, or uniform cost search, iterative deepening depth first search. Okay, so accordingly, it can be informed search strategy, it can be adversarial search strategies. So it matters a lot. Okay, and yes, cannot take advantage of the problem decomposition. Like the basic problem solving strategy that we used to follow is divide and conquer. Means divide your problem into sub problems, then solve each sub problem independent of each other, and then try to conquer, that is merge the solutions of those sub problems in order to get the final solution to the major problem. Okay, so accordingly now you can see one example, like some tasks are considered over here. So like the task is get milk, bananas, and cordless drill. So standard search algorithm seems to fail miserably in this case. So we have to find out the reason, because it starts with the activity, like who is responsible for what, so who is going to perform this particular tasks, and when those tasks will be executed or performed by that individual, and third thing, in which scenario, on what particular day, on what timings, or at what timings these tasks are to be executed. Okay, so in this way we can have this arrangement in graphical format. So you can see, like here, it is quite essential to know the initial state, as it is required for any complex engineering problem as of now. So it is quite essential to know the like from where we have to start. Okay, so like we will have some initial state, and we'll have some final state, or the set of final states again associated with it, and multiple intermediate or intermittent states. So like as per the situation, or depending on the situation, planning problem can be defined. Okay, so in real world, without prior knowledge, like we can end up in searching exhaustively for the particular finished state, that is this goal state. We can see, or you can assume, like this particular finished state. Oh, okay, so this is nothing but the goal state. So we can consider the example of like a problem solving agent, which are also known as planning agent or goal based agent. See, exhaustive search is required to reach the goal. And why these search strategies are executed in the problem search space? Because from the set of available solutions, we have to select the best possible solution or the optimal solution which are available with us. Okay, so to reach the goal or to reach the objective, it would typically be a search that may have to traverse back and reapply of the actions. You might have gone through the problems like n queens problem. For example, for 8 queens problem, like backtracking strategy from algorithms, problem solving strategies can be used. Like we can backtrack to some extent, and like we can get the things done again from that particular state, and there is no need to again start with the initial state or start state. Okay, so I hope all of you are getting this. Like if you are not getting some stuff, feel free to ask me. You can interrupt me at any point of time. I hope the things are like you are getting the things and you are understanding the things properly. Okay, so this should not be it is humble request to all of you, this should not be a one-way communication only. This should be a two-way communication, so that you will greatly benefited out of this session. That is nothing but the agenda behind the today's session. All right, so yes, so how nice it would be if we were to have some heuristic function or some heuristic before taking any decision. In real life, it is just not possible all the time, because some things we can pre-plan, but of course we have to make decisions timely uh, in some cases. Okay, so if we could have the problem divided into different tasks, so it would make the things simpler. Okay, so having some guidelines or instructions as to how to travel to the goal state or finish final state in this case, with some intermediate states known, it would make it much better. Okay, so considering all these situations, there is a need to have some planning to solve the problems optimally. Okay, so this is again one of the classic example you can consider. So problem decomposition is the phase that we have already studied, but before that, let us discuss what is the exact role of planning in case of artificial intelligence as a whole. So see, intelligent systems or intelligent agents, which are nothing but the decision support systems that need to be aware of what is to be done and how it can be done in real time scenario or in real world life environment. So planning allows us exploring different possibilities, like it makes intelligent agents or intelligent systems more flexible, and hence it increases the decision making capabilities too. Okay, so in order to plan, the problem needs to be well understood. So do remember from exam point of view also, this is important point, like what is the exact role of planning or where planning comes. Like whenever we consider this flow, like what exactly the artificial intelligence is, different definitions associated with artificial intelligence, then games, game playing or problem solving strategies, concept of search space, the knowledge representation, reasoning, planning. So this planning, or in order to plan, the problem needs to be well understood by problem solver. So planning requires proper representation of what needs to be achieved. Okay, so it involves reasoning as well, which you have studied in the previous unit, that is unit number 5, as well as it needs techniques which are applied to solve that particular problem. So planning plays a major role in various tasks, like you can consider robotics, specific military tasks, or some industry 4 standards also, where digitization of all those processes is going on. So let's have a detailed discussion on this concept of planning. So the basic planning problem, it starts with actually the question with like how to go to the next state or to the goal state, that is finished state, from the exact state. And we have studied like we need some transition function for moving from the current state to the next state. Okay, so being on or being in a current state or in some particular state, whenever we receive some things, so we will make some decision, like in that particular state what we are reading or what we are getting, that is going to be the input, and accordingly in connection with or forming the scape pair between input and current state, we are going to have the decision like to move towards or to roam towards the next state. Okay, so as we have just discussed, it involves two things, how and when. Okay, what was our first question, like how we are going to achieve this. Okay, how we are going to achieve this particular thing. And second question is when. Okay, who is responsible for it and when it is required to be executed. Okay, so it definitely involves selecting appropriate action and sequencing those actions so that the required actions is invoked in some proper sequence. Okay, so we can make the things more clear and more technical through this discussion. Like, so planning problem is defined with some domain model, initial state and goal state. So problem decomposition is the state after we like finalize the domain or model the problem in terms of or with the terminologies from that particular domain. So domain model defines the actions along with the objects, and it is quite necessary to specify the operators that actually describe the actions. Along with that, information. Okay, so see, data is what everything which is available with us. But whenever we associate some meaning or when there is some meaning associated with that data, so it becomes information. Then when we organize the things or when we put up the things with some experience associated with it, so automatically it will become the knowledge. Like information is represented in terms of knowledge, and in next phase of knowledge representation, it becomes the wisdom. Okay, so in that case, like we can give, like I can give example. Knowledge is what, how to make use of gun. If suppose you are having a gun with you, so how to like trigger that gun and how to make use of it is nothing but the knowledge associated with it about the gun. But when you have to perform this is nothing but the wisdom, and that is more important. Okay, I hope you are getting. Okay, so these entities like goal state, initial state, these formulates the domain model. And initial state is what? Of course, it is the state where any action is yet to take place, like the stage when exam schedule is put up. Like, okay, in or in this scenario, you can simply consider this example of examination schedule. And final state will be what? Like the goal state is the state which the plan is intended to achieve. So it constitutes all the facts that will be true once your plan gets completed, like till your results get declared for this particular semester. Okay, so outcome will be what? Like the final result will be getting all clear in the subjects. That is nothing but the goal. Okay, so we work on a strategy that actually forms the plan, and the decision of the sequence in which the actions are performed is a plan. So the components of a planning system, so it majorly deals with problem decomposition. So as it is mentioned, the partial order planner is based on the assumption that most real world problems are nearly decomposable. Okay, working on some sub goal may undo another sub goal even. Okay, so this is again one of the important point of discussion, like planning versus problem solving. Somebody may say like this, yes, in problem solving also we used to plan, or we used to have initial states, some intermediate states, some goal states, that is final states. So what is the difference between this planning and problem solving? Okay, so it starts with planning agent is very similar to problem solving agent, which are also known as goal based agent or planning agent. You you may remember this thing, like problem solving agents, which we have studied in unit number 2 of this course, artificial intelligence. So those problem solving agents are also known as goal based agents or planning agents. Okay, so these planning agents constructs plans to achieve goals, and then they execute those things. Okay, so planning agent is quite different from problem solving agent in terms of like representation of goals, states, and actions, use of explicit logical representations, and the way it reaches to the final solutions. Okay, so defining a goal, like goal is initially set by the agent, is important task. Then planning, like plan is built, and taking action, that is actions are invoked as per the plan. So the process continues each time with some new goals, and things are simple to understand in the planning agent. So it is the same way we decide when we have some goal which is already set. But since it is an agent environment, so there have to be some assumptions, like recollect some environment types an agent that has. So what does an agent assume in this case? So see, first case is the actions occur one at a time. So there should be no concurrent or parallel execution in this case, and that this cannot be further divided. So there is no uncertainty, and the agent is well versed with the outcome that is specified with the action. Third thing is rules or things which are not specified are assumed to be false. Okay, and fourth thing is the agent's action that causes the changes or modifications in the current state, and the knowledge that has, or it has the knowledge about it. So the environment is of the type fully observable. Okay, so do remember this key difference between planning and problem solving. Next, you can consider these examples. So planning systems do these things, divide and conquer the things or problem. Relax requirement for sequential construction of solutions. And yes, of course, for problem solutions, you can consider like states, actions, goal, and plan. If you consider these 4 factors, so you can see like data structures in problem solving, and in case of planning, we will be having like logical sentences which are associated with it. In case of actions, you will have code, okay, that is preconditions or outcomes which are associated with it. Then goal thing is like it is a code again, and the analogous thing in planning is the logical sentences that are again with it. and plan is like sequence from S0 to some other states, and the planning is like constraints which are in line with it along with those particular set of actions. Okay, so this is quite famous problem solver task, missionaries and cannibals. It is mentioned in our textbooks and reference books too. So like we start with some initial state, and if suppose we have to achieve this thing, so you might have studied the 8 puzzle problem where total 9 positions are provided, and we are given with 8 tiles. So one position is blank, and we have to start our journey from initial state, and of course we have to reach to the final goal state again, which is mentioned within the problem statement. So you can see, like, if suppose we start with this 331 in this particular example. So these are the possible combinations or expansions, what we can say, that we can have, and this particular line or branches we can further expand in this particular case. So like it depends on the ultimate goal state that you have to achieve throughout this journey. So this is again the famous problem. So next example is planning based approach to robot control. So job of planner is generate a goal to achieve and then construct a plan to achieve it from the current state. So of course we have to come up with these 4 things. So for any problem statement, do remember this. You have to define the actions, you have to come up with states, some goals associated with it, and your plans. Okay, so it must come up with this representations. Okay, so actions like to generate successor state, descriptions by defining preconditions and post conditions, which are nothing but the effects of that particular actions which when executed. So those will be the actions, nothing but the actions. States are simply the data structure representations which will describe the current situation. So what exactly we are getting or reading as an input, what we are supposed to produce as an output, it also deals with it, and how we are going to process it, that is the procedure. So that again deals with the states. Okay. A third thing is goals, like what we have to achieve. So what is to be achieved, it dealing with it, and plans is the solution, that is a sequence of actions which when followed will take us to the final goal state. Okay, so this is again a good example. You can elaborate the things with it. So now whenever we look towards some historical developments, so many AI planners, they are mentioned over here. So well-known AI planners, they are strips, which we are going to discuss in subsequent slides for some time. So theorem proving system, app strips, added hierarchy of abstractions, that is keeping the things hidden, more important things hidden rather. So we have to just briefly give the details regarding your plans, and from where we are going to start and from where or how we are going to achieve the final goal state. That will be the agenda. And hacker again use library of procedures to plan, and NOAH, that is problem decomposition and plan reorder. These are some what we can say the typical AI planners that we can go through. So strips based approach to robot control. So in this case, like first order logic, you might have studied this concept, which is the type of the predicate logic. Okay, propositional logic, predicate logic, first order logic. You might have discussed or studied these things in knowledge representation unit number 4. So use first order logic and theorem proving to plan strategies from start to goal. And strips language is, of course, we will discuss now, like it is Stanford Research Institute problem solver. So this is AI problem solver given by, as its name suggests, it is Stanford Research Institute problem solver. So this acronym is, so this is nothing but S stands for Stanford, ST rather, R is research, I is institute, and PS is problem solver. So a restrictive way to express states, actions, goals, and plans, but it leads to more efficiency and more effectivity in solving the problems. All right. So would like to ask whether you are getting the things or not. Please share your feedback. All students do respond, please, whether you are getting or not.
You can unmute yourself and you can ask.
Please unmute yourself and respond if you are getting, so that we can proceed further. Are you getting?
Students, sir is asking something. If you are getting, you have to
Please
say yes or
respond.
no.
Yes, sir.
Yes. Okay. Okay. Thanks. Okay. So I hope all of you are getting, and let us start. Continue with our discussion. So before that, like before going through this languages, see, these are nothing but the planning languages. This comes under planning languages. So first of all, I would like to discuss this. I hope you can see my screen. Somebody, can you please confirm whether you are getting?
Yes, sir.
Yes, sir, it's visible.
Can you see the whiteboard over here?
Yes, sir.
Whiteboard, not PPT, right?
Yes, sir, it's visible. Jamboard.
Okay. So see, the planning languages comes into picture first. Okay. So deal with it like after briefing about the representation. Just now we have discussed the type of representation, like how goals are represented, how actions are represented. So goal is most often a partially specified state. So state or say proposition, or that is said to achieve or satisfy the given goal. If it consists of all the objects which are required for the goal, or maybe some other information too. Okay. And action representation is again like some preconditions, post conditions, and how we are proceeding further. So whenever we decide to do something, so we are aware of the state which in which we are currently, and what possibly the effects would be for that particular state. All right. So when it comes to the mapping of the actions for an agent, or in case of robots, for example, just now we have discussed. So the pre and post situations needs to be specified. So your PEAS environment, if you remember those PEAS criteria, like performance, environment, actuators, and like sensors. So accordingly, for any case study like vacuum cleaner or driverless automatic car, Google car, you can consider as an example, classic example. So we can have these activities mentioned in terms of some languages. So whenever we have to plan, okay, so see, we know that language is the thing that should be expressive. Okay, and language comes up with grammar. So again, referring to the earlier discussion of representation. So do we need the language? So the answer is yes, we need the language. Okay, so every planning language makes use of representation schema so that algorithms can be operated on it. Okay, so like some typical languages I would like to mention. So you can consider first is strips. Okay, so it is Stanford research. Let me make this T capital. ST, Stanford Research Institute. problem solver. Okay. Second point is like second type of or second planning language is ADL. It is nothing but the action description language. And third thing is, you do remember this type of like planning languages, PDDL. It stands for planning domain description language. Okay, so let's start with this discussion, like Stanford Research Institute problem solver scripts. So it's a language that is historically important, and as we have discussed, on this slide, you can see. Is it visible slide now?
Yes, sir, it's visible.
Yes. Okay, fine. So it was developed in 1970s at Stanford Research Institute for the first intelligent robot that they have developed. So scientists, researchers, and practitioners have make use of it. So it makes use of the first order logic predicates. So the representation structure that we have discussed earlier with the first order logic in unit number 4 while studying knowledge representation. So it essentially belongs to this strips. So you might have idea about this. What is this? Can anybody tell what this symbol refers to? Can anybody tell? Can anybody tell? What does it mean? This highlighted symbol, whether it is conjunction, disjunction, and or. Have you gone through this?
Conjunction.
Have you studied this stuff?
You can unmute yourself and give the answer.
Please do respond, guys. Don't be passive, okay?
Conjunction.
Is it conjunction? Are you sure?
Yes, sir.
Yes, it is conjunction. Next symbol is what?
Negation.
Negation. Very good, very good. Negation. Yes. Okay. So conjunction, disjunction, negation implies that is one directional, two directional, it is bidirectional representation. So this type of things are used while representing the production rules for any given problem. So the restrictive way to express this states, actions, and goals is the facility provided by this particular planning language. So states, as it is mentioned, like conjunctions of ground, function tree, and positive literals such as at home and have banana. Okay, so closed world assumption is used over here. Okay, so strips allows function free literals. Okay, for better understanding of strips planning language, you can consider this example. So as planning, the planning discussed is related to the agent's environment. So we have the typical example of robot. The example involves the robot, cup of tea, some guests in your living room, and let us say you have 2 rooms. Okay, so you can consider the example, like do listen carefully to this example. So if suppose you have the robot with you, so the cup of tea, guests, and 2 rooms, and you want the robot to get the tea and give it to the serve it to the guest. Okay, so we can represent these things through strips. Okay, like initial and final states, of course. So whenever we start with this representation, so the possible states which you can represent over here. So let me open next page. So you can consider like see the possible states for this case studies. This will be first, you can consider in as a function, let's say. So robot and room number 1, let's say R1. Okay, and in, let's say T, you are along with T in room 2, suppose. Okay, and guest also using in function, let us say guest, again they are in room 2. R1 and R2, these are room numbers. R1 is room 1 and R2 is room 2. Okay, second possible state we can have is in robot R1 room, in T, let's say it is again R1 room, and guests are also in room number R1. Okay, and third thing is, let us replace it by room 2. Let's say we are having robot in room 2, T in room 1, and in guests in room 1, and so on. Like it's a use list. It can be used list like any or every permutation and combination of this type, like all three entities like robot, T, and guest, and the rooms associated with, like available with us, R1 and R2. So see, let us say that goal state is guests are in room 2. Let me highlight this. Okay, so if suppose this is your goal or goal state. Okay, so if suppose, or let's say for this case, let me select this as a goal state, this as a goal. If suppose this is your goal state, all right. So possibly you can consider or define, set some preconditions and post conditions with it. Okay, so preconditions we may say like those are constraints. Okay, we have studied constraint satisfaction problems. If you remember CSP, best example is cryptarithmetic logic, send plus more is equal to money, those kind of problem, or 2 plus 2 4. Okay, you might have studied these problems. So these preconditions are created as constraints, and post conditions are nothing but the things which, whenever you will achieve the goal state or final state, so those things that you will have after achieving the goal state. So there can be other actions like in this case, pick the cup of tea, where the robot is in room number 2, let's say, and T is also in room number 2, and the post condition will be like hold that T by robot. So in such action, delete list can be empty, which is again valid. Okay, so in this manner, strips makes use of lists. Okay, strips uses lists, actions, and third is operands. Okay, so this is the way. Then it comes to syntax and semantics. So now this is nothing but the syntax, let us say, for a particular language, AI language, let us say. So in is function, and these are the parameters like the thing or object and room number. Okay, so this is regarding syntax. Whenever it comes to semantics, that is meaning which is associated with it. So the precondition is false, let's say. So the action cannot or may not occur as state does not exist and it cannot be applied. But do remember the order in which the add and delete lists operate is very much important. Okay, so we can conclude in case of strips, Stanford Research Institute problem solver language. It is easy to understand. Use of propositional logic makes the implementation and building of knowledge base easy. And due to this, inference engine or reasoning also by the knowledge representer becomes simple. But do remember, knowledge is very much restricted. Okay, it assumes propositions in limited numbers. So as we are applying these terms, constraints, so it matters. Okay, so this can be a major drawback when considered with a different domain where there could be more involvement of large number of propositions. Okay, so this is nothing but the stuff regarding the strips. So here some other examples are also mentioned, like conjunction of literals. You can see here at home function, conjunction not having bananas, and at x position, like for example market, and sells x comma bananas. So states, goals, and actions. I'm highlighting this. See, states, goals, and actions. So actions is again preconditions, like constraints or limitations that just now we have discussed, that must hold before execution and the effects after execution. So post conditions are nothing but the effects which are the which comes along with simply the post conditions outputs. So this is strips action schema you can consider. So it includes action name and parameter list. So precondition and effect. These are nothing but the post conditions. So I hope all of you are clear with this and we can move further. Okay. So all of you have understood, I think, and there is no issue with this strips. So Shaki's strips world is an again example. So do remember, because I'm going to give a small assignment as an exercise again after some time. So do understand these things. You have to perform that task during this session. So move from one place to another place or search space to another search space. So go to door s comma dx. So precondition is in room s comma rk and connect dx comma rk comma array. Effect is add list next to s comma dx and delete list none. Go through doors is another function. So in this way, we can mention the things in terms of algorithms, in terms of flowchart, in terms of pseudocode, etc. Okay, so representation level, like at knowledge level representation, your logical level representation, your implementation level representation, it may be different, but the concept of planning needs these things like preconditions, post conditions, actions, states, effects, which we have mentioned over here. So those representations are quite important. So here you can see at start state and goal state, they should be like this. So we have to pick up this particular A block, which is mentioned in blue color, and we have to pick up this from over here, from here, and we have to put it on to the block B. So this was the start state or initial state, what we can see, or and this is going to be the goal state. So the journey is nothing but needs planning. So accordingly, those planning things, simple example, it is mentioned through strips. You can see those things over here. Okay, all right. So these are the challenges of AI and planning from the viewpoint of planning. First is closed world assumption. So assumes that world model contains everything the robot needs to know. So there can be no surprise. Okay. And frame problem is how to represent real world situations in a way or in a manner that is computationally tractable. Now, principle of tractability, it comes with the principle of optimality and principle of rationality, which we have discussed in unit 2 and unit 1 respectively. Okay, so these are the challenges, what we can say, and researchers and practitioners are continuously believing and doing their works in this area so that we can come up with the proper solutions in the literature. Okay. So next point is planning algorithms with the state space search. So the planning algorithms is the most straightforward approach is to use and make use of state space search. So progression, which is also known as forward state space search, and regression, which is also known as backward state space search. Okay, so problem formulation for progression. Let's have a discussion on this. Before that, would like to again get back to our whiteboard screen, Jamboard, let us say, and let us have a discussion on this ADL also and PDDL, that is Action Description Language and Planning Domain Description Language. Okay. Okay. So second point is ADL. Now, in case of ADL, see, as strips planning language lacks the expressive power. So that drawback is, like, we can consider this as an extension of strips. So it is overcome with the use of action description language. So it can be extended very well to overcome some of the limitations, and ADL, like action description language, does that. Okay. So the beauty of this action description language is, first, it allows negative values or negative literals to, okay, it allows negative literals. Second, it makes use of qualified and quantified variables with conjunctions and disjunctions. All right. Third is conditional post conditions are allowed over here. Which was not the case with strips. And fourth is variables with different types can be used over here. Okay, so I have not added this stuff in PPT, today's presentation, but still you just do remember this key differences, or how they differ, like, or how they are like extended or expanded furthermore next to the strips. Okay, so you can consider any example and again mention the scenario using ADL following these rules. Like, so do remember these are the characteristics or features of or properties of ADL, and of course the next point is, it is PDDL, Planning Domain Description Language. So it is PDDL, third type. So it is the standardization of planning language, and it is defined by researchers and practitioners as the standard language. So we can treat this as a superset of previous two languages, superset of strips and PDL. Okay, superset concept. Are you aware of this? Superset concept. Okay, so it has properties like objects can have type specifications, okay, can have negative preconditions too, along with post conditions, which we had in earlier case, action description language ADL. So now we can have negative preconditions too, provided like before execution. Negative preconditions assumptions is also possible. Add delist lists. They can be conditional. Okay. And in some cases, it permits us or it allows us to make use of numeric values. Okay, so it allows numeric values. Do remember these things only from your better understanding point of view. So PDDL, that is planning domain description language, is used in case of classical planning tasks, and planning tasks in PDDL. They are separated into domain file and problem file. So domain will be different part. We'll have knowledge of domain as an domain knowledge representation you can consider, and problem file, it will deal with the inference engine, like related to the problem or some other, what we can say, the supportive stuff that we can have in this case, right? So let us again go back to our PPT. So problem formulation for progression, this we have already discussed. So initial state, actions, goal test, and step cost, like path cost, each action is one. If we are considering each path age, associated weight is one with it. All right. So yes. Next is progression. So plan is a sequence of strips operators. So from initial state, search forward by selecting operators whose preconditions can be unified with literals in the state. New state can be identified and they can be introduced, like while planning as a state space search. So progression planning you can consider. So planning starts with initial state and it proceeds with search. So it follows the effects of possible actions. And yes, sequence of actions is considered till we are able to build or form a sequence to reach the particular goal. Okay, so start state or initial state of the problem prior to any action applied to it, and it assumes that the things are which are not mentioned, like objects which are not involved, are not true. Okay, and goal check or goal test, what we can see, which is mentioned over here. So it is goal test, whether the state satisfies the goal of the planning, checking of whether the goal is achieved, reached, or not achieved, not reached. Okay. Regarding actions, see, we are done with this as in start state, initial state. Goal test, it is nothing but the path or goal check also. Actions applicable to the current state, actions preconditions are satisfied. So it involves the list or sequence of actions with respect to the preconditions that allows moving to the next intermediate state, of course. and step cost is each action is 1. So it is a cost associated with every action that is taken. So most oftenly you can consider this. It is just like the path cost concept from problem solving agent or goal based agent or planning agent. So we had in BFS, IDDFS, DFS, uniform cost search, depth limited search, we were having this path cost initially set to 1. Okay, so see, any of the search method that comes to the solution, if at all exists, so it is complete in nature. Okay, whenever it comes to like checking completeness or checking the optimality, so like it is created as the uh, complete thing, complete case. Okay, so complete planning algorithm is possible to obtain, but there are many drawbacks of such search. Okay, so see, scenario is simple with limited number of propositions, but what will happen if number of propositions is increased or some preconditions, post conditions are increased? So it is also observed that actions that are considered in the planning, they are all the possible actions, and there is quite emerging possibility that irrelevant actions not leading to the goal, they are carried out. So for understanding, uh, I can give you the example, like which example? Yeah, let us consider the same example again. If suppose in upcoming end semester examinations, SPPU examinations, suppose you are planning for getting more than 80% marks, okay, and you are focusing on some topics that are out of syllabus or some points which are never asked in previous university question papers, let's say, okay. So as you are unaware of these things, so you study those things also, the contents beyond syllabus, let us say, or some points which are never asked in the exam. Okay, some such points which are never asked. So therefore, they are also taken in the planning. So you are planning for studying those topics. So if you have the knowledge, the plan can be made better. So here heuristic function concept comes into picture. So will this or can this forward planning be made more efficient with the aid of heuristic? Okay. So yes, we have discussed these things. So this is nothing but the idea behind forward planning. Okay. Or progression through these logics. Now let us discuss about regression, that is regression planning, which is also known as or backward state space search. For the previous was the forward state space search. Now this is going to be the backward state space search. Dear students, please do ask your doubts. If you are having any queries, please do ask. These things are quite important from understanding point of view. So in advanced artificial intelligence, of course, you are going to make use of these things in your industrial informatics and throughout your career also. Okay, so do try to understand and get the things in proper way. Okay, so in case of regression planning, the exact reverse process is applied that we had in progression. That is, excuse me.
Dear students, you can unmute and ask your questions, or you can even put your questions in the chat box. Okay. If you have any queries, you can put your questions in the chat box as well.
Extremely sorry for the interruption. Am I audible? Somebody please confirm.
Yes, sir. Yes, sir.
Yes, sir.
Okay, okay. Yes, so we were discussing the concept of regression, that is the exact reverse process of progression, that is forward state space search. So this is going to be the backward state space search, which is also known as the backward chaining from goal state. Kindly excuse me once again for a minute. Yes. To plan, like search is started from the goal state. If you remember, we have studied the concept of forward engineering and reverse engineering in case of like in software engineering course. So it is just similar like that. So we can move like towards the intermediate or pre-states from the goal state all the way. But now here in this case, the question is, how can we reach the pre-states? Like from goal state, not from initial state. Do remember this difference. In earlier case, we used to start from initial state, but now in this case, we are going to start from the goal state. So how we can reach to pre-states? It is not the case like we are just having only one or two pre-states or intermediate states. So how can we reach the pre-states? Okay, so it is there is a two-step procedure. So we can follow that. In first step, we can select the action. Do listen this very carefully. First is we can select the action that satisfies all of the propositions or some of the propositions in the goal state. I repeat once again, we can select the action which satisfies all of the propositions or some of the propositions relevant to the goal state. And second thing is you can reform the goal or new goal again, so that that can be treated as the next what we can say the pre-states or intermediate states. All right. So like this is an example which we have already discussed, worked on through this Jamboard. We have discussed this example. Now let us go for the heuristics for state space search. So see, the goal propositions that are satisfied by invoking the actions, they can be eliminated, whereas unsolved ones, they can be keep intact. So the precondition is a state which is prior, so that can be added. So these two steps which we have discussed just now, they can be repeated unless and until the initial state or start state is achieved or reached. As we are going backward in reverse way, so we have to start our journey from goal state and we are going back to initial state or start state or initial state. So see, do remember the way in which we are representing the propositions they are achieved is very much important here. That is, ordering is very important. You should execute the actions in some proper sequence only. And main advantage of backward search is that the relevant actions are considered. Okay, like some sub actions or sub activities which are involved within that process. So we used to take cognizance or we give importance to those relevant states or actions also, or activities or functions also. So they are taken into consideration. So any of the search strategy can be made use of in the process of planning. So let us proceed towards the discussion of heuristics now. So how to find an admissible heuristic estimate? So see, we have discussed two methods, progression and regression. in previous slides. This is progression, that is forward state space search, and regression is backward state space search. So you might have seen during this discussion. So see, progression and regression planning can be made efficient and effective with the use of heuristics. So do you think that is it possible to identify the number of steps or the actions to be executed so that goal is achieved? So if you have any idea about the types of problems like P problem and NP problem, so NP problems are again further categorized into NP hard and NP complete problems. So P problems are nothing but the polynomial time problems, like total time taken by problems. If you can represent the time in terms of polynomial, so those are P problems, and NP problems are those different problems. Like so, this comes out to be the type of NP hard problem. So now this is not the topic of our discussion, today's content. So let us not discuss and further elaborate these things in terms of NP hard and NP complete and P problems. So some solutions we can discuss like. So what we intend to do is to find out the admissible heuristic function. Okay, so we can simply convert the problem into relaxed type of problem. So all the preconditions can be removed, like we can remove all constraints or limitations, and you can come up with just like relaxed type of problem or simple problem representation. This is one way, and another way is like you can assume the thing, you can consider. See, relaxed problem that we have discussed, and second thing is sub goal independence assumption. That is, you can assume that the sub goals are independent, so that the total cost in all to solve the problem is approximated by summation of the costs, where sub goals are solved independently. Okay, so the cost of solving a conjunction of sub goals is approximated by sum of the costs of solving each sub goal independently is important. And in summary, in conclusion, I can say like the progressive and regressive planning actions, they are dependent on the sequences, and there is a need to have planners that can consider sub goals, solve them independently, and then final plan can be combinations of the sub results that are obtained. So we can proceed for partial order planning now. So relaxation problem is idea is removing all preconditions from the action. So almost implies that the number of steps required to solve a conjunction of goals is number of unsatisfied goals. There may be two actions, each of which deletes the goal different or literal achieved by the other, or some action may achieve multiple goals. And combining relaxation with sub goal independent assumption, exact of unsatisfied goals, and removing negative effects that we have already discussed through empty delete list heuristic, and quite accurate, but computing it involves running a simple planning algorithm. So generate a relaxed problem by removing negative effects. Okay, so these things we have already discussed in case of action description language. So state, open world assumptions, effects, goals, effects, equality, predicate can mention in this way. So one example is mentioned again, air cargo transport through this ADL representation. So, like action description language, we can represent the things. So here, see, you can represent these things this way. See, init, at, C1, SFO, JFK. So these are nothing but the loading, unloading cargo plane onto off planes and flying it from place to place. So actions are load, unload, and fly, and these are the states. So accordingly, using conjunction, disjunction, implies, directional, that is bidirectional, negation, we can mention this conditions. All right. So I hope this is also clear to all of you. Okay. So next is space tire problem. Again, similar thing. some sample problems which we have already discussed now, previous slides. Then comes the total order planning. So forward, backward state space searches, they are form of totally ordered plan search in all system as a whole. Let us discuss partial order planning. So whenever we discuss this partial order planning, so see, in partial order planning, like partial order planner will help, and search problem formulation for partial order planner that we will discuss through the example. So idea is the concept of total order planner we have gone through, like any planner that maintains the solution. It can be partial solution, approximate solution, or within some range of solutions, or the exact best possible optimal solution. So the planner maintains the solution as a totally ordered steps that it has identified so far, forms a linear plan in case of total order planning. Okay, whereas if we go partially, as its name suggests, in partial order planning, if we go partially, we are able to put up the ordering constraints temporarily, and hence it is referred as partial order planning. So with progressive and regressive plannings that are linear in nature and are often referred to as totally ordered, there is a necessity to have the plannings to exploit the sub-problem structure. Okay, so we can consider the problem, this pop example. Just a minute. Yes. So suppose we have to put on a pair of shoes. So goal is what? Right shoes on and left shoes on. Initialize. After initialization, action is right shoe. So precondition is what? Right socks on. Effect is right shoe on. Like whenever we have weared the right or socks in right hand, right leg, so we will have like right shoe on. Action is right sock. Precondition, nothing. Effect is right sock on. Action, left shoe. Similar case now in case of for left shoe, precondition is left leg should have socks weared, and effect is left shoe on. Action is left sock. Precondition is nothing, and effect is left socks on. Okay. Also, you can consider another example that I can give as door latch, where you have to latch the door. So with the use of lock and keys, total order plan and partial order plan, you can give the solution. So list commitment strategy, it can be like policy, treated as a policy where decisions or choices, they are delayed. So it simply says that it guides us like do not make any decisions unless and until they are required. Okay, so there are advantages of this type and disadvantages also. So one advantages of using this is that it avoids rework. Okay, tasks might have to be undone. So to understand the concept, you can like consider the example in academics also. Assume that some assignment is given to you for a particular course for artificial intelligence, let us say, and you have to complete the assignment on the same day, like today itself. Okay, but suppose assignment does not get getting evaluated from the same course teacher. Okay, your subject teacher till deadline, or say some grades regarding submission, they have been put up online through Moodle or some Google Classroom or some Microsoft Teams platform, let us say. So like we can hope in this case like rework would be avoided. Okay, so in case of partial order plans, in this case study, The plans are created by making search through plan spaces, and it follows the list commitment strategy. So this strategy allows to make choices relevant to current solvable part of problem. Okay, so the question is again, how can the partial order plan be actually represented? So answer is in the form of graphs. Typically, graph is the best type of data structure, what we can say. Some special types of graphs like tree, they can be used for this. POP comprises partial order planning, ordering rather. So in this case, it comprises temporal constraints also. So these constraints or preconditions, and they specify that some state X is before state Y. So in POP, pre-order, like partial order planning, you can consider in case of partial order planning POP, the planning algorithm can put two or more actions into a plan where sequence in which actions are to be carried out does not really matter. Okay, so the same example is given, like we are starting from this initial state, this is finished state. So from start, left sock, this is flow for left leg, and this is the flow for right leg. Okay, so I hope all of you are clear with this. So these are total order plans which are best possible for this. So out of this, you can go for best possible or optimal solution. Okay, so how this work is mentioned in the form of propositional logic or predicate logic also. So initial plan, these things we have discussed just now. And successor functions, all of you are quite aware of this. These are nothing but the actions. So these functions helps us to, or it takes us from initial state or start state to the goal state or final state. Our goal test is there are no open preconditions for this. So final plan, one example is mentioned again with the same case study. And example algorithm, again you can mention all these things in terms of algorithm, so which will return plan. If you remember the algorithm for problem solving agent or goal based or planning agent, so it was like it is supposed to return action or some failure, let us say. Okay, by considering input as the problem and the problem solving strategy. So these two parameters we are supposed to forward, or we are supposed to pass to this function. Now in case of partial order planning, POP is an acronym for it. Do remember this POP is nothing but partial order planning. POP is an acronym for it. So in case of totally order planning and partial order planning, you can have an algorithm for it. So it is a sound complete partial order planner using scripts representation. So function is POP, initial state, goal state, operators which are associated with it, returns plan. So plan implies make minimal plan, initial to goal state, loop, do if solution, plan, then return plan. If it is not, it is needed. So select sub goal, pass plan, and choose operator, plan operators as need comma C, and resolve threads plan, take us to end. Okay, so this is an example. Of course, I'll share this slide so you can go through the slides thoroughly at your end and understand the things. So again, for flat tire, that cargo flight reservation and that case study, that example, the detailed partial order planning is mentioned over here through using predicate logics or first order logics. So these are the strengths. Casual links lead to early pruning of alpha beta pruning. You might have studied, so you are quite aware of this pruning word. So for portions of the search space because of irresolvable conflicts, and solution is partial order plan, that is linearizations produce flexible plans. Now let's have one activity exercise. I hope all of you are clear with this. So we have done with this difference problem solvers and versus planners, that is planning versus problem solving. So this is somewhat summary from my side regarding planning problems. So planning agents make use of look ahead to find out actions to contribute to goal achievement. Planning agents differ from problem solvers in their use of more flexible representations of states, actions, goals, and path or plans, path costs or plan costs. The strips language describes actions in terms of preconditions and effects, that is post conditions. Preconditions are, of course, the constraints or limitations. And principle of least commitment is preferred. Partially ordered planning is a sound and complete algorithm for planning using strips representation, that is Stanford Research Institute problem solver representation. So now let's have one interesting activity. This is an exercise for you, and then we'll proceed with the next thing. So we will have 5 minutes with you. I'll read this exercise. You have to perform this activity. So see, monkey and bananas problem is faced by a monkey in a lab with some bananas hanging out of reach from the ceiling. So a box is available that will enable the monkeys to reach the bananas if he climbs on it. Initially, monkeys is at A, bananas at B, and box is at C. Do remember this. A is variable for monkey, B is for bananas, and C is for box. I repeat once again, A is for monkeys, B is for bananas, and C is for box. The monkeys and box have height low, but if monkey climbs onto the box, he will have height high, the same as the bananas. Okay, so actions are mentioned over here. Go from one place to another, push an object from one place to another, climb up onto or climb up down. These are the successor functions or actions from an object. Grasp or ungrasp an object, and the results of a grasp is that monkey holds the object if the monkey and objects are in the same place at the same height. Okay, so these are 3 questions. You have to write down the initial state description for this. Write down the goal state, like monkey has banana at location B on the ground. And third thing is ABC were defined. And third thing is you have to write down the 6 action schemas for this. Okay, so you have 5 minutes with you. Okay, this is break time, you can consider. And yes, of course, please try to write down these things at your end. And we'll start with the next step. Some real-time applications, and few stuff is remaining again from planning. So we will quickly have a discussion on those topics like planning graphs and other things. So till the time for next 5 minutes, please do try to write down answers for these 3 questions and get the things done. All right. So let's have a 5 minutes break. You can consider. But in this, you try to write down these things on your own for this. I'm giving you like this activity is mentioned over here in brief. Now actions are also mentioned clearly, and these are the questions. So try to define initial and goal states and write down 6 action schemas based on these actions or some successor functions or actions which are mentioned over here, successor functions and actions.
Hello, students. Have you done with your exercise? Hello. Has anyone completed the exercise?
Is it done?
I guess they have completed, but they are not answering. Yes, ma'am. We can check that in the classrooms, right? So, sir, you may continue with the further session.
Sure, madam. Sure. All right. So I hope all of you have done this and enjoyed this exercise. So also, continuation with that, I have two more exercises for you. So describe the differences and similarities between problem solving and planning, and explain why dropping negative effects from every action schema in a planning problem results in a relaxed problem. So do try to solve this at your end. Now let's move towards the next topic of discussion, that is planning domain. So in planning domains, like it is regarding the concept of continuous planning, multi-agent planning, classical planning, completeness, incompleteness, correctness, incorrectness, reactive planning. So classical planning, where the plan is prepared typically. So it is like it works in fully observable, static and deterministic environment, and actions are correct and complete. In case of incompleteness, they're in partially observable, non-deterministic, or it can be combination of both. And incorrectness, the world does not necessarily match the model of the world. Okay. So again, whenever we see the towards these things from the viewpoint of bounded, unbounded, sorry, indeterminacy, that is from the viewpoint of characteristics of environment. So bounded indeterminacy, actions have unpredictable effects, but the possible effects can be listed in the action description axioms. So it can be like planning under uncertainty. So rather than building the plan with the branches, it makes use of the things like if then rules. So what different exactly they are doing? So in case of such kind of planners, they are based on the concept that they should be able to handle unknown situations also. So the reaction rules are used that help them in doing so, but there is also a need or requirement to have reasoning while applying the reaction rules. So again, bounded indeterminacy and unbounded indeterminacy deals with this. So these are four planning methods for handling indeterminacy: sensorless planning, execution monitoring and replanning, conditional planning, and continuous planning. So we will not go into much more details of it, because as their name suggests, they are quite clear. Sensorless planning, like it constructs sequential plans to be executed without percepting anything, because we are quite aware of this thing, like the sensors are responsible for perceiving the things from the environment in real time. And then actuators are responsible for performing actions after like goals, states, and like process whenever we follow in case of problem solving, goal based, or uh, planning agents. Okay, so sensorless planning, like no physical and chemical changes inside the environments. They will not be anymore tracked or monitored in real time. So time factor is not critical in this case, and that is going to be the like sensorless planning. Okay, in case of conditional planning, like contingency planning, you can consider just now we have discussed. So it constructs a conditional plan with different branches for different contingencies which are associated with it that could happen. In case of execution monitoring and replanning, it makes use of preceding techniques to construct the plan, but it monitors and keep tracks on the execution process, and overall it replans the things whenever they are like it is necessary. And continuous planning, like continuous planner is designed to persist over a lifetime. So it can be thought of as a planning wherein the monitoring and replanning activities, they are clubbed together. So in case of continuous planners, the operation is incremental in nature. So by incremental, we mean that plan formulation is dependent on current perspective, and continuous planning agent always begins with this percept and generates the plan. So at each point of time, percept is observed and plan is generated. So the methodology is incremental in nature. Okay, so like we can consider again the same scenario that we have discussed in partial order planning, for that example of wearing shoes in right and left legs. You can discuss or elaborate the things on your own. Okay, so example scenario again is mentioned over here for all those typical types. So we are quite familiar with or job shop scheduling problem. You might have heard about it. So while going through the slides, the coloring problem, graph coloring problem. Okay, so no two adjacent areas or regions will have similar color. So accordingly, we have to achieve this particular goal. So similarly, the job shop scheduling problem, like it is a problem that needs to be handled in following some time constraints, scheduling, and at the same time has to perform check on the availability of resources. So job shop problem consists of n number of jobs that are to be completed, and to complete those jobs, some machines are available with us, and for the jobs to get complete, there is a sequence of actions, set of actions, n number of actions which are required to take place on the machines. So we are going to have total 3 sets. First set will be n number of jobs, second is n number of machines, and third is n number of actions. Okay, so see, every action has a specific duration, and it might make use of some resources also. So the problem is to minimize the time required for the completion of the jobs, and at the same time we have to handle the resources constraints if at all they are in. So do remember there are some variants for job shop problem also, job scheduling problem. Okay, so like is it a scheduling problem, like does it require some planning? So the answer is yes. Answer is yes, because job shop scheduling problem occurs in case of production scheduling. So there is a requirement or need to have an appropriate planning so that constraints are taken care of. Okay, and you can properly plan or schedule the jobs and do the things, execute the things properly. Okay, so again it can be represented good in terms of Gantt chart from project management, but here we will not discuss again that concept of Gantt chart. So it is about we are here to talk about planning and constraints. So we will take the things ahead in the constraint parts only. Okay, so in proper way we have to assemble the things. So coloring problem again can be mentioned. Likewise, sensorless planning, contingent planning, replanning, and vacuum world. Like this example you might have studied, like we are having these two areas where dirty particles things, they are present in both of these spaces, and vacuum cleaner is over here. So we can have like single state or multi-state agents. So in case of this vacuum world or vacuum cleaner example, so we can have such states. So some of the states, like we will have some one initial state and goal state. Other states will go under intermittent states. So any one of this, like we can have any of the combinations of this, and we can again move further with this. So it is in the right place, like vacuum cleaner is placed in the right place. This is also fine. This is also fine. This is not the fine. Like we have to first of all move this vacuum cleaner into the space, and then we can get this area or region get cleaned. Same case is over here. This is okay. This is okay. Like we are having vacuum cleaners, but no dirty things or particles. Dirty things or particles, they are present in any of the region. Okay. So simply we can move in this way or in this direction in achieving the final goal state. So this is typical, what we can say. Let me maximize this. So see, whenever we start with this combinations, so either we can move in left hand side, like vacuum cleaner can move in left hand side, in right hand side, or can stay as it is in the same region. So here these are the possible combinations. So these can be treated as some states, okay, or actions, activities, okay, and accordingly the transitions or their movements, like they can be defined, and we can achieve the ultimate state. All right. So this you might have gone through in first unit only. So again, same example I have created or considered. So this is conditional planning in fully observable environments. So of course, fully observability and non-deterministicness. So what is non-deterministic is what deterministic is, which there is a one way, like, or one possible way only to move from initial state to goal state. No other ways are given. So there is a deterministic way from one state to other state. That is not the case with non-deterministic. So in case of non-deterministic, wherever there is logical path possible, so logically you can put up the edge, and you can move from the current state to the next state. Okay. So that is nothing but the non-deterministic. So fully observability means that agent always knows the current state, and non-deterministic is, it is nothing but the openness or concept of clearness. That is, everything is clear to us. And in case of non-deterministic, because the agent cannot predict the outcome of its actions, it is not firm at each and every time, instance of time. All right. So with this, again, disjunctive conditional effects, now you can represent. This is the syntax. So when this is the condition, so the effect will be S2. So using this representation, you can simply represent the your schema, data schema, again through this production rules. So vacuum cleaner that may dump dirt on the destination square when it moves, but only if that square is clean. So action left precondition colon alt at R effect comma at L, that is at right and at left, or at left and when clean left side colon not clean left side. So this is nothing but its representation in predicate logic, first order logic, isn't it? So accordingly, you can have conditional plans ready with us. So plans becomes trees again whenever we create or we represent these things in the form of graphs. So in general, condition plans should work regardless of which action outcomes actually occur. So it is all about like hierarchical planning. You can consider where heuristics also comes into picture, or planning graphs concept. Like after having an elaborated study of all these types of planning, planning graphs is what it is concept introduced in 1990s, around 1995. I don't remember exactly, but I think it is in 1990s. You can check in reference also. So planning graph is data structure simple that encodes auxiliary data structure that encodes the information contained within the states regarding their reachability. So the basic idea is to construct smaller size graphs that would contain partial information about the reachability. Then what is reachability? So that reachability means estimate or costing about the steps required to reach a particular state from the initial state. Okay, so you can consider this example. See, I'm highlighting. Consider the vacuum cleaner. Initial state has a robot in the right square of a clean world. The environment is fully observable. Goal state has the robot in the left square of a clean world. It sometimes deposits dirt when it moves to a clean destination square, and sometimes deposit dirt if suck is applied to a clean square. Okay, so this way, like by use of algorithms like graph plan is one of the algorithms. So it is possible to get a direct solution from the planning graphs. So planning graph you can simply create as it looks like this. Okay, you can see, and it is like comprising of states and actions that form layer and they appear alternatively. So it can be represented as the combination of states and actions too. Okay, so this is also known as subtree. So it has a goal node at every leaf, specifies one action at each of its state nodes, and includes every outcome branch at its chance nodes. Okay, so and or graph. So Minimax algorithm you might have studied. Have you studied this algorithm, Minimax? Do you remember this algorithm? Please respond. Everyone, am I audible? Please respond. Have you studied Minimax algorithm?
Yes, sir.
Yes, studied. So do you remember Minimax algorithm concept? Finding out minimum of the value at a particular state, then going for max value at next particular label. Are you aware of this?
Yes, sir.
Yes, sir.
Okay, so I'll consider this that you are quite aware of this fact, and we'll go for this discussion like applying rules in the form of and or graph. So in case of this and or graph, max and means node becomes or and nodes respectively. So max means what? Or here, and mean means what? And accordingly the rest part is same, like it is quite similar as that of the planning graphs, and accordingly we will have the conditional plan as it will be written by these graphs. So the plan needs to take some action at every state but must handle every outcome for the actions that it takes. Okay, so the algorithm needs to return a conditional plan rather than just a single move. So at an or node, plan is just the action selected. At and node, the plan is nested series or if then else loop steps specifying subplans for each outcome. Okay, like more than one solutions are possible. So in that case, you can make use of this and or graph. So this is the and or graph search algorithm. Okay, so you can see this is function problem as a parameter to return a conditional plan as it is mentioned in the previous slide. See, it returns a conditional plan. It returns is the conditional plan rather than just a single move. All right. So function is or search and this is and search. So accordingly, similar things are mentioned in terms of actions and plans over here. Okay. We have time constraints, so let us move further. We have already discussed this. This is an example again. You can go through this at your end. Yes, we have discussed this conditional planning in partially observable environments. So we can represent this using and or graphs this way. So left either you can move So this is clean left, not clean left. So this is the scenario. So from A as an initial state, you can have either B or C. And whenever we expand B, like, so for right case, you can have either clean R or not clean R, that is right side. And the operations like suck, movement in right, left side, clean left or right side. So these are mentioned in this graphs. Right. So belief states, again, we have discussed the agent's belief state is what? Like it is fully observable, that belief state. Regarding agents, we have discussed. So standard fully observable problem solving is just a special case in which every belief state is a singleton state containing one physical state. So you can consider and see this example set of full state descriptor. So yeah. So at R and clean R and clean L, comma at R and clean R and not clean L. So it is large belief states. Okay. So this is about representation of intermittent states. How sensing works. So it is automatic and active. So at every time step, the agent gets all the available percepts. So time factor is critical over here. And active sensing, the percepts are obtained only by executing specific sensory actions such as check dirt and check location. And don't go for clean left, clean right, or other like operations unless and until we receive the next notifications. Okay. So action description using knowledge propositions. So again, it is like in terms of production rules, they are mentioned. So agent, intelligent agent, how it will work or how it will mention those sensings, they are mentioned over here. So I think now, yeah, this is one more point important, visualize the process. So this way you can have like the detailed procedure. So this is the whole plan as a system as a whole. Okay? The whole system as a whole whenever we consider. So this is going to be the whole plan and this is the systematic or partial plan in that you can consider. So you can just continue with the same process unless and until you achieve the goal state or you reach to the goal state. So till the time you can just follow those things. You can carry on like the things accordingly. Like it is mentioned over here, you can see agent executes the plan until this state E. Before executing the remaining plan, it checks preconditions as usual and finds that it is actually in state or the state O rather than state E. And yes, it then repairs the plan so that it can get from O to some point P on the original plan, and new plan is the concatenation of repair and continuation. So now this will be your new plan. So from this whole plan now, we will not have any part of these two states, do remember, and we will have like flow from O to G directly, not from start state, from O state to G state, that is goal state. Okay. So I think all of you are clear with this. Again, this is a famous example, blocks word example. It is mentioned in our textbook and reference book also. So you can refer it, this example, particularly blocks example. So this blocks world problem is what it says. You can see the initial state and goal state is mentioned over here, and our typical task is we have to start from initial state and reach to the goal state. So you can see some blocks, they are placed on the platform, okay, or on the table. But you can see again, it is very easy problem, okay, blocks problem, as it is shown over here. So it is easy thing. Start state is A and goal state is D. So the goal state is on C comma D and on D comma B. So that is nothing but the output that we have to achieve. Okay. So that is we have to attain, okay, as a goal state. So elementary problem is that like framing problem in artificial intelligence is concerned with the question of what piece of knowledge or information is pertinent to the situation. So like elementary assumptions can be made, and we can typically like from state A, we can think like from this particular state, if we have to reach to this. So what like movements or pick the things, skip down the things. So such operations in this block puzzle or block world example is also known as block puzzle problem too. So we can achieve the goal state. So the hand run is given over here. You can see from start state to finish state. So here you can see from start state, like on table we are having A, on B comma E, like E is at the bottom and B is at the top. So on C comma F, like C is placed on the F, on D comma G, D is placed on the G. Clear A, clear C, clear B, and clear D. These are the situations, okay, or positions, what we can say at the initial state. Now, as we have to achieve this, so what we have to do is, first of all, we have to keep this D over here onto the B. So we have to take this or pick this D from here, and we have to keep it over here. So on D, G, clear D, clear B. So we have to move D to B. Means what? This D will be moved to the top of the B. Getting or not? Say yes or no. Please say yes or no.
Yes, Govinda, you can reply.
No, sir.
Okay, fine. Okay. See, we are towards the like concluding end. So yes. Similarly, for next case, as we want C, which is at its current state, situated or placed on the position on the F block. So we have to move this C from C to top of the D. So move C comma D you can consider, and hence it is on C comma D on D comma B, which is finished final state. So initial plan is constructed by the continuous planning agent, just like other normal partial order planner. Okay, so accordingly you can achieve the final state. Continuous planning, again it is mentioned. So please do find time at your end and go through this handrun or this illustration which is shown. Simulation results in detail, it is mentioned on these slides. So please go through this at your end. So this way we are reaching to the goal state from initial state to goal state. So in all, this is nothing but the summary of planning. So summarize regarding the planning concept, you can say like with the necessity of for the planning in artificial intelligence in the fully observable environment as well as under uncertainty, planning is most important task. And planning system consists of goal states, initial states, actions to achieve them. So the actions are represented in the form of operators to achieve the goal, and the representation for a planning system has to be very effective. Different languages like scripts, ADL, they are used for planning. Approaches like goal state planning and the means ends analysis show their characteristic with the scripts. The state space search and forward backward state space searches like progression and regression searches that we have studied. Progression, regression, state space searches, they assist us in the selection of particular action. Addition of heuristics makes the planning more effective and efficient. So see, planning is not just concerned with the organization of tasks, but forms the basis for reasoning. And after like that, we can give proper reasoning to it, and we can go for, like, it acts as a plinth, what we can say, for reasoning. So partial order planning approaches prove to be better option than that of the total ordering planning, which helps us in building partially and parallel executable plans. And the list commitment strategy adds benefits to the partial order planning. Further, we have just now discussed the concept of planning graphs and or graphs. So they help in determining the reachability of a state, and the term of mutex tackles the constraints. And hierarchical planning, conditional planning, this conditional plans, execution monitoring, replanning agent, continuous planning. So the concepts of non-linear planning also, they're important when it comes to handle the real-time complex problems. Okay, so like it is widely used in research at present for gaming purposes, also gamification, whereas multi-agent planning finds its place in various domains like military tasks, vehicle assembly, or industry 4.0 standards, like where we are automizing the things, okay, where mathematical background comes into picture. So typically, like, we can have several applications, so range of applications. So to discuss with that, like, these are several domains or areas of AI, and some interdependency is shown over here. So journey starts from search. You can see they are interdependent amongst each other, and logic, knowledge representation, reasoning, machine learning, planning, natural language processing, computer vision, robotics, expert systems, and the list is huge, unending. Like, it is soft computing, deep learning, neural networks, artificial neural networks, convolutional neural networks. And of course, AI is, like, artificial intelligence is the key role player in modeling the things in the best possible way at its current state on today's
Hello,
day.
sir. Sorry to disturb you.
Yes, madam.
Yes, sir. We have a more 5 minutes in which we need to conclude because they have another session too.
Yes, madam. For
Yes.
sure. Sure. Yeah. These are some applications, areas, what we can say, where, like, in intelligent transport systems, whatever it may be, it can be robotics, in game playing, e-learning based systems, warehouse optimization, in agriculture industries too. We are having a set of applications. So we'll just have a quick overview of these applications: autonomous planning and scheduling, autonomous rovers, so satellites, innovations, so monitoring and control applications, forecasting applications, like for decision making and forecasting. So these are most important aspects of our life, and whether it is weather forecast or it is related to some professional or personal decision. So we are very keen on the decisions or to get to know about something. So artificial intelligence plays important role in forecasting also, and it will also be in the application as identification of employee in payroll management system, who would be, like, committed to the company. Further, again, in business trends also, there are huge set of applications. So autonomous planning and scheduling, telescope scheduling is another area, satellite analysis of data, medicine, image guided surgery. So this is again another emerging trend or thrust area in healthcare systems. So artificial intelligence and medical domain, they have been closely associated for range of years. And expert systems assist in diagnosis and providing guidelines for medication in real time also through e-healthcare systems. Even though the intelligent system can be web-based, the expert systems has often proved to be accurate in diagnosis. So medical practitioners even agree with the decisions provided by AI systems. So for cancer analysis, cancer detection, identification of genetic disorders, other diagnosis, for ECGs, EEGs, electrocardiograms, like AI is essential. Okay, so again, image analysis and enhancements you can consider. Document management systems, web-based intelligent systems, in intelligent transport systems, autonomous vehicle control. So travel is inevitable to everyone nowadays, and whether it is for business purpose or leisure, we need to have some good roads, short distances, good restaurants on the path or on the way to take halts, and so on. So intelligent transport system is one way, like it can assist us in the travel using AI. So we people make use of Google Maps. Okay, so you can imagine, like if suppose we are roaming without having Google Maps and you don't have any idea about your destination address. So without GPS, global positioning system for mobile communication, bus or train. So like would give the waiting time for next coming uh, uh, destination or place station. So it is in real time, of course. Time is critical factor once again. So considering the possible issues that would arise in the travel. So road transport is again a good example of this. Pedestrian detection, uh, like in case of automated car, driverless car, you can consider automated driverless car. So pedestrian detection is must. Accordingly, your PES environment will give input. In games, gamification also classic example of this. So role of AI is very much important in games also. So typically we have gone through this case studies. In robots also, robotics is another domain. So in robotics, even we are having like the application of artificial intelligence thoroughly. And last but not the least, these are some other applications where we can have, like in planning and scheduling, image analysis and classification, language processing, speech recognition, speech to text, text to speech conversion, sales analysis, forecasting, weather forecasting as we have discussed, data warehouse optimization, space transformations, natural language processing, and the list is huge. So in all, in such a way, we can have like in future also, intelligent systems do have the great future. And yes, the approaches and the case studies that we have discussed throughout this course, and like it helps us in building a picture on how artificial intelligence is making its position in every industry nowadays. And really, artificial intelligence is contributing towards industrial growth. So every time, every day, new dimensions are added up to have better systems with a huge contribution from AI. So it is very difficult to say that only specific industries or areas they are able to make use of artificial intelligence. Answer is no, as almost everything that we wish to have, we feel it needs to possess intelligence, that too machine intelligence. So last but not the least, I would like to say thank you to organizers, the department, Professor Dr. Darshan V sir, and Bora madam, Madam Kedar madam, giving me this great opportunity to share my knowledge
Tishala,
and to discuss
mute yourself.
students. I'm very happy to help you and support you again in upcoming future too. And let us keep in touch in this way also. So happy learning to all of you. If students, anybody is having any doubts, please do let me know and do share with your feedbacks. I'm very much like eager to receive and hear from you people regarding this session. So thank you very much, all of you, for your time and patiently listening. Thanks a lot. Thank you, madam. Have a nice time ahead, all of you. Thank you.
Thank you, sir. It's time for vote of thanks now. I, Professor N.S. Khirnar, take this opportunity to propose vote of thanks for today's session. I thank Professor Dr. Darshan Medhane, sir, for accepting our invitation for this expert talk on planning and real-time applications of AI. Really, the session was so live, informative, and knowledgeable, sir. I also thank our honorable management, Principal Dr. M.D. Kokate, sir, Vice Principal and Head Dr. M.R. Sangvi, sir, for permitting us to arrange such kind of sessions. Last but not least, I also thanks my dear students for patience listening. At the last, I just request you, Dr. Medhane, sir, to please share the contents like PPTs and all with us so that we can share with our students.
Sure, madam. Sure.
Okay, sir. Thank you once again for
Yes.
such a wonderful session, sir. Thank you.
QR code is given. Students, you can give your feedback using link or using the QR code. Thank you once again, sir.
Thank you, ma'am. Thanks a lot.